In this video, we're going to talk about the derivative and how it relates to a graphical quantity called the tangent line to a graph. So once again, this is day 2 of talking about what derivatives are conceptually, all before we really get a convenient way to calculate derivatives. By the end of today, we should be able to give an informal definition of what are called the secant lines and tangent lines to a graph. We should be able to describe a relationship between the average rate of change and the slope of a so-called secant line. We should be able to relate the derivative, aka the instantaneous rate of change, to the slope of a tangent line. And we should be able to find the equation of the tangent line to a point. So when someone says the secant line to a graph, or a secant line to a graph, this is just a line that passes through 2 points on the graph. So here we have an example of a secant line to the function x squared. It's passing through the 2 points on the graph, one where x is 1 and y is 1 squared, 1 squared being 1, and the other point being the point where x is 2 and y is 2 squared, which is 4. The function x squared is of course this cyan parabola, and the secant line, whose formula is given here, is this orange line that's passing between these two labeled points, secant line. Now, notice that if the line passes through 2 points on the graph, one of which has an x-coordinate of x1 and one of which has the coordinate of x2, then the corresponding y values of those points on the graph have to be f of x1 and f of x2 respectively. Because in order for a point to be on the graph, the y-coordinate has to be equal to the output of the function at that given x value. So let's consider what the slope would be for the secant line passing through these 2 points on the graph of a function f of x, one point where the x is equal to x1, and another point where the x is equal to x2. So the slope formula is given by rise over run, where the rise is the difference of the two y values and the run is the difference of the two x values. So if we take the second y and subtract the first y, and divide that by the second x, take away the first x, then this would be the slope of the secant line passing through these 2 points on the graph. Does this formula seem kind of familiar? This formula is exactly the same thing that we gave for the average rate of change. This formula is exactly the same as the formula for the average rate of change of the function f of x on the interval from x1 to x2. Store that in memory just for a second, and let's consider what's called a tangent line to a graph. A tangent line to a graph crosses the graph in one position and which has the same slope, or generally the same slant, as the function at that point. So here, for example, is the function f of x equals x squared once again, and this time we've drawn a different line in orange. We've drawn the tangent line to the graph at the single point 1, 1. The defining features of this tangent line are that 1, the tangent line and the graph both contain this shared point 1, 1. So the tangent line and the curve share this white point in common. And not only that, the second thing that a tangent line has to do is at the location 1, 1, the general slope or slant of the line has to match the general slope or slant of the curve. So both of them are almost overlapping, almost doing the exact same thing in the vicinity of the point 1, 1. So here would be another example of a tangent line. In this case, we have the function sine of x, graphed in blue. And I'm considering the location on the graph where x is pi over 2 and the y value is 1, 1 being equal to sine of pi over 2. At that location, the graph of sine of x is basically flat because we're at the absolute top of this hill. The tangent line is also flat at that location, and the tangent line passes through this point pi over 2, 1. So the tangent line and the graph share this point in common, and the tangent line and the graph have, roughly speaking, the same slant or the same slope at that location. Now, depending on where you decide to anchor or position your tangent line, the slope of the tangent line can vary. So I've just set up a quick slider here so that you can see that as the point at which we attach the line to the graph changes, the slope of the tangent line also changes, so that the slope of the tangent line will always be an exact match to the slope of the graph itself. Notice as well that if I position the tangent line so that it's attached to the point, roughly speaking, back here, it is okay if the tangent line crosses the graph at more than one point. All that matters is that the tangent line is attached to the graph at least one location, and at that location the graph's slant and the line slant are the same. Now there's an interesting graphical relationship between the secant line and the tangent line. Here I am on Desmos, and currently I have graphed the function, and in white I have also graphed the secant line to this function through 2 points. One of those points is anchored here down at 1, 0, and one of these points is anchored up here at 2.6, 1.28, roughly speaking. Now what I'm going to do is use a slider to ever so slowly move this right-hand point closer and closer toward this anchor point here at 1, 0. Watch what happens to the secant line as I move that right point in. In we go. The right point gets closer and closer to 1. Now, I have drawn it so that the right end point and the left end point have basically completely coincided. And when I did that, what happened to the secant line? As the right endpoint moved in toward the left endpoint, the secant line transformed into the tangent line. As the second point approaches the first, as that right point gets closer to the left point, the secant line becomes tangent. So what mathematical tool have we used in the previous videos to have the right end point of an interval get closer and closer to the left end point of an interval? When you want one quantity to approach a second quantity, we have used a limit. And in particular, if we wanted to get a formula to give us the slope of a tangent line at a point such as x equals a, we could take the formula for a secant line through x equals a, I could anchor the secant line to the function at one point where the x value is a, and at some other point close to a, take the slope of the secant line through those 2 points, and then apply a limit. We could let the right point get closer and closer to the left point, and by doing that, the secant line transforms into a tangent line. But again, this is a formula that we've seen before. The formula for the slope of the secant line was identical to the formula for the average rate of change. The formula for the slope of the tangent line is identical to the formula that we had for the instantaneous rate of change. Which is this quantity that we call the derivative for short. So the big takeaway from this entire discussion is that the derivative of a function f of x at x equals a, that number on the one hand is equal to the instantaneous rate of change of a function, but it has another significance. The value of f prime of a is equal to the slope of the tangent line to f of x at x equals a. Now, why is this something that might matter? Well, we'll get into more detail about why this is significant as the days go along. But one reason why this is fantastic is that it's really easy to tell just from the graph of a function whether the slope of its tangent line is positive or negative. Which means, as a result, that you can tell in advance whether the derivative should be a positive or negative number well before you ever have to go through this long process of finding the derivative using the difference quotient formula. It's easy to tell whether f prime of a should be positive or negative. All you have to do is go to the graph of your function, look at what the tangent line would probably be, and determine if the tangent line has a positive slope or a negative slope. So let me give you a quick example. Here is a function f of x. We don't even have a formula for f of x, so it would not even be possible to calculate the value of the derivative by hand. Nevertheless, from this picture alone, we can determine the sign of the derivative, whether it's positive or negative, at each of the following points without doing any calculations. For example, let's consider the point marked A over here on the left side. I'm going to go ahead and I'm going to sketch in a possible tangent line to the graph at A. The tangent line is going to be attached to the graph at that location and is going to be pointing in, roughly speaking, the same direction as the function. So here is a rough sketch of a tangent line at A, a straight line which is just grazing, just sort of kissing the graph at A and then moving on. Now this line points downward. It has a negative slope because as you increase x, you have to decrease y in order to get back onto the line. So at the point marked A, the slope of the tangent line is negative. And as a result, the derivative is doing the exact same thing. So, derivative is negative. All of this without ever actually having to calculate the derivative using that nasty formula. Let's try it on the next point labeled B. The point labeled B is down here. And the point labeled B is actually at the very bottom of this sort of valley in the graph. If I wanted to sketch a tangent line at point B, in order to make the line tangent, the line would have to be horizontal, because the graph has leveled off at point B. So here in green is a sketch of a tangent line to the function, and that tangent line has 0 slope because it's horizontal. So at point B, the tangent line has 0 slope, so the derivative would be equal to 0. This is a manifestation of the fact that the graph at the point B was roughly speaking flat. At the point C, if we sketch in a tangent line at C, this time this tangent line is pointing to the upward direction. If you increase a little bit, y will increase as well. So the tangent line has positive slope, and therefore the derivative is positive at C. At the point D, once again, we're at a location where the graph is flattened off, which means that the tangent line is going to be horizontal. At the point D, the derivative will be 0. What do you think about point E? At point E, the graph is sloped downward, so the tangent line will be sloped downward. Therefore, the derivative will be negative at this point as well. At point F, the graph is slanted upward, and therefore the tangent line will also be slanted upward. Therefore, the derivative at point F will be positive. Let's apply that principle to a problem like this one. We've got a function f of t, which in this problem measures the position of a moving object at time t. And we don't have any really information about the formula for this function. All we have is the graph, and I should note here that this graph stops at time t equals 0, and this graph actually stops at time t equals 4. So only 4 time units, maybe 4 seconds is passing, and that's where we're measuring this object's position. Now, without the formula for the function, let's see if we can answer the following questions. Based on the data here, when is the object moving in the forward direction? When is the object moving backward? And when is the object stationary? Now, recall from yesterday that if an object was moving forward, we captured that by using a positive velocity. Also remember from yesterday that the velocity was the derivative of position. So really, in answering this question, we're asking, where is the derivative of the position function positive? In such locations, the velocity of the object will be positive, and that's the feature of an object moving in the forward direction. Well, now we have another way of conceptually understanding the derivative. The derivative is the slope of the tangent line. It's basically the graph's slant. So What I'm really looking for in this graph are locations where the graph is slanted upward, where the slope of the tangent line is positive. So let's have a look on the graph and let's see if we can figure out during which times the graph was slanted upward so that the slope of the tangent line, which is equal to the derivative, which is equal to the velocity, where those quantities are positive numbers. So here is our graph. And I'm noticing that between this position, where x is equal to 0.7, and this position, where x is equal to 2, the graph overall is slanted upward. If I take the tangent line to the graph, at any position between those two locations, any tangent line I draw will have a positive slope. So it looks like the object is moving forward between 0.7 and 2. But that's not the only location on this graph with this property. If I look at the locations to the right of this point 3.5, at all of these locations, the graph is slanted upward. So at all of these locations, the tangent line would have positive slope, therefore the derivative would be positive, therefore the velocity would be positive. And as a result, the object would be moving forward. So between t equals 3.5 and the final time at t equals 4, when was the object moving backward? At such a location, the velocity would be a negative number. So the derivative would be a negative number, and therefore the slope would be a negative number. So we're looking for locations where the tangent line would have a negative slope, which forces the graph to be tilted down. Now looking at the graph, I see two more locations where overall the graph is pointed downward. The first location is that between the initial time at time t equals 0 and this bottommost point at time 0.7, if I draw any tangent line to the graph, between those 2 points, the slope of that tangent line will be negative. So I could say between t equals 0 and t equals 0.7. That would be one location, that would be one time interval where the slope of the tangent line is negative and therefore the object is moving backward. Likewise, over here between the point at 2 and the point at 3.5, once again, any tangent line I draw in this location will have a downward tilt, and therefore the velocity will be negative at those locations, and the object will be moving in the backward direction. Now someone says, are there any moments in this object's journey when the object is basically stationary? Now if moving forward is a positive velocity and moving backward is a negative velocity, standing still represents a velocity of 0. So we're looking for locations where the derivative is equal to 0 exactly. We're looking therefore for locations where the slope of the tangent line is equal to 0 exactly. And as a result, we're looking for locations where the tangent line would be perfectly horizontal. let's look at the points that occur at the bottom of these valleys and at the top of these hills. At the bottom of the valleys and at the top of the hills, the graph flattens out. And at those locations, the tangent line to the function is horizontal. So based on the image here, there are 3 instances when the car's speedometer, when the object's velocity is measuring 0 exactly. At time 0.7, at time 2, and at time 3.5. The 3 locations on the graph where the tangent line was horizontal. Now imagine the problem of trying to find not just the slope of the tangent line, but also to find the equation of the tangent line. In order to find the equation of a line, you usually need 2 ingredients. 1, you need the line's slope, and 2, you need a point on the line. Now for a tangent line, we actually have a lot of information about those 2 things. We know that the slope of the tangent line at x equals a is given by the derivative of the function at x equals a. And remember, we called this in mathematical notation f with an apostrophe parenthesis a, f prime of a. Part of the definition of the tangent line was also that the tangent line and the function shared a point in common. So the point where x is a and y is the function's output at a is a point on the tangent line. They share this point in common. Let's work on finding the equation of the tangent line to f of x equals x squared at the location where x is minus 1. Now the slope of the line is given by the derivative of the function at the given a value. So I'm going to find the value of f prime at the a value of minus 1, which, as you recall, was the limit as h approaches 0 of f of minus 1 plus h plus f of minus 1 divided by h. Now we did a calculation very similar to this yesterday. F of minus 1 is minus 1 squared, which is positive 1. F of minus 1 plus h is minus 1 plus h squared, which can be simplified to positive 1, negative 2h, positive h squared. So putting that information into this formula gives us 1 minus 2h plus h squared minus 1 all over h, which can be simplified first to negative 2h plus h squared over h, and then when you cancel common factors, negative 2 plus h. Now that this is fully simplified, we can plug in h equals 0 and we get minus 2. So the slope of the tangent line is the value of the derivative is minus 2. The point on the line is given by a and then f evaluated at a. The a value was given to us as minus 1. When I plug minus 1 into the function, that gives us minus 1 squared, which is positive 1. So now we have a point on the line and we have a slope of the line, so we can find the equation of the line using whatever technique you prefer from algebra. Generally speaking, my favorite way to find the equation of a line, given the point and given the slope, is to use the point-slope formula. Which says that you can take y minus the y of your point equals m, and multiply that by x minus the x of your point. So in our case, our point has x equals -1. Our point has y equals +1. And we found that the slope of the line was -2. So what's the equation of our line? The equation of our line is y minus 1 equals -2 x plus 1, or if you like, y equals -2 x plus 1 plus 1. You can simplify it further if you want to, but that's not strictly speaking necessary. So let's just quickly confirm what we found. Here is the graph of the function f of x equals x squared, and here is the point on the graph where x is equal to -1. If we calculated our tangent line equation correctly, then we should see that tangent line up with the graph at x equals -1. The line should pass through this point, and it should have the same slant as the graph at that point. So let's try it. We found y equals -1 x plus 1 plus 1, and sure enough, that pink line is doing exactly what we want. The pink line is attached to x squared at this location, and the pink line is tangent to the graph. It has the same slope as the graph. So that concludes today's material. Today we learned that, yesterday we introduced the derivative as the instantaneous rate of change of a function. But the derivative has another meaning. The derivative is the same thing as the slope of a tangent line to the function. That relationship has a couple of different uses. First of all, that means that it's possible to determine the sign of the derivative really just by looking at the graph of the function. If the function's graph is pointed downward, then we know that the derivative should be negative. If the function's graph is pointed upward, then we know that the derivative should be positive. And if the function's graph is flat, then we know that the derivative should be equal to 0 exactly. We also looked at how to use the difference quotient for the derivative to calculate the slope of the tangent line, and then how to go one step further and find the entire equation of the tangent line, usually using the point-slope formula.